What if we're not alone? It's one of the oldest, most profound questions humanity has ever asked, a question that has echoed through centuries of stargazing, myth-making, and scientific wonder. Out there, in the silent expanse of space, lies the tantalizing possibility that we are not the only living beings in this universe. And today, that question is no longer just the stuff of dreams or science fiction. We are living in an era where astronomers are closer than ever to finding an answer. Picture the cosmos not as an empty, dark void, but as a sprawling cosmic ocean dotted with islands of possibility. Worlds with conditions just right for life, planets where liquid water might flow, where atmospheres might swirl with the chemical signatures of living processes. The search for these alien worlds has become one of the greatest scientific adventures of our time, driven by powerful telescopes, brilliant minds, and an insatiable human curiosity to understand our place in the universe. In this video, we're going to embark on a journey to 25 of the most promising exoplanets, worlds beyond our solar system that could harbor life. From scorching super-Earths to icy ocean moons, each of these distant orbs holds secrets that could reshape everything we know about biology, existence, and our cosmic significance. So settle in, open your mind to the possibilities, and join us as we explore these potential oases in the vast cosmic desert. The answers are out there, and the search has only just begun. Our journey begins practically in our own cosmic backyard with a world known as Proxima Centauri b. Imagine stepping outside on a clear night and gazing up at the constellation Centaurus. There, invisible to the naked eye, is a faint red star called Proxima Centauri, and orbiting it is the closest known exoplanet to Earth, a mere 4.2 light-years away. In the vast scale of our galaxy, that is an astonishingly short distance, making this world our immediate next-door neighbor in the Milky Way. What makes Proxima Centauri b so compelling is its location within what astronomers call the habitable zone. This is that special region around a star where conditions might be just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. And since water is the one ingredient essential to all life as we understand it, this placement immediately puts Proxima Centauri b on the shortlist of promising candidates. It's also a rocky world with a mass believed to be about 1.2 times that of Earth, suggesting a similar, possibly familiar terrain. But life in this neighboring system would face extraordinary challenges. Proxima Centauri is a red dwarf star, a type far smaller and cooler than our Sun. Because of this, for the planet to be warm enough for liquid water, it must orbit extremely close to its star. One likely consequence of this intimate dance is a phenomenon known as tidal locking. Much like our moon is locked with one face always pointing toward Earth, Proxima Centauri b may have one hemisphere in perpetual, blistering daylight while the other is frozen in eternal night. The most promising place for life in such an environment might be in the slim, temperate borderland between these two extreme worlds, the so-called Terminator line. There is another, more violent hurdle. Red dwarf stars are notoriously tempestuous, frequently erupting with massive stellar flares that bombard any nearby planets with intense ultraviolet and X-ray radiation. These blasts could strip away a planet's atmosphere over time and bathe its surface in levels of radiation that would be lethal to most known life forms. The question for scientists is whether Proxima b could possess a strong magnetic field or a sufficiently thick atmosphere to shield any potential life from this harsh stellar weather. Despite these daunting obstacles, its incredible proximity makes it our most tangible target for future exploration. Projects like Breakthrough Starshot envision sending tiny, laser-propelled probes on a flyby mission that could reach this system within a few decades. Getting a closer look is no longer a distant fantasy but a conceivable goal for the next generation. holding the potential to provide our first direct evidence of an environment beyond our solar system that could harbor the chemistry of life. Leaving our closest neighbor behind, we venture just a little farther into the cosmos, about 40 light-years away, to a star system that utterly redefines what a solar system can be. Here, orbiting a faint Jupiter-sized star, is TRAPPIST-1, a family of 7 rocky worlds so compact that if you were standing on the surface of one, the neighboring planets would appear in your sky not as distant points of light, but as clear, magnificent orbs, some even larger than our own moon appears to us. And of these 7 incredible siblings, one stands out as a prime candidate in the search for life, the world known as TRAPPIST-1e. What makes this planet such a rock star in the astronomy community? It checks nearly every box on our wish list. TRAPPIST-1e is almost identical in size to our own planet and has a very similar density, which strongly suggests it's a rocky world with a solid surface, a place where, hypothetically, you could stand. Most excitingly, it orbits right in the middle of its star's habitable zone. This is that Goldilocks region where temperatures could be just right for liquid water to pool and flow on the surface, not so hot that it boils away and not so cold that it remains permanently frozen. The star it orbits, TRAPPIST-1, is an ultra-cool red dwarf. This means it's far smaller and cooler than our Sun, and as a result, its habitable zone is incredibly close in. All 7 planets orbit closer to their star than Mercury does to our Sun. A year on TRAPPIST-1e, one full trip around its star passes in just 6 Earth days. This proximity raises questions similar to those for Proxima b, like the potential for tidal locking. However, the unique gravitational dance of these 7 worlds, all pulling on each other, might actually generate enough internal heat through friction to keep their interiors warm and active, potentially powering volcanic activity or even sustaining a liquid water ocean beneath a thick crust of ice. This system is a gift to modern astronomy because the planets orbit so frequently and transit or pass in front of their star from our point of view so often, we have an unprecedented opportunity to study their atmospheres. Each time a planet transits, starlight filters through its atmosphere, allowing telescopes like the James Webb Space Telescope to analyze that light and detect the chemical fingerprints of the gases present. Scientists are eagerly watching for signs of water vapor, methane, oxygen, or even complex molecules that could hint at biological processes. Finding such a combination of gases would be a potential game changer, the strongest hint yet that we are not alone. TRAPPIST-1e isn't just a single world of interest, it's part of a cosmic laboratory, offering us a chance to study 7 different examples of how planets form and evolve around a common star, dramatically expanding our understanding of where life might take hold. Now we travel 500 light-years from Earth to a discovery that truly shifted our perspective on what might be out there, the landmark world of Kepler-186f. Before its discovery in 2014, we knew of plenty of large gas giants and a handful of so-called super-Earths orbiting within their stars' habitable zones, but finding one that was almost a perfect Earth twin in size. That remained an elusive dream. Kepler-186f was the breakthrough, the very first rocky planet we ever found that was nearly identical in size to our own world, and crucially, orbiting comfortably within that life-giving region where liquid water could exist. It was the proof of concept we desperately needed, a signal that planets like ours weren't just theoretical possibilities but actual, verifiable realities scattered throughout the cosmos. Located in the constellation Cygnus, the Swan, this planet is part of a 5-planet system orbiting a red dwarf star significantly smaller and cooler than our Sun. Much like the worlds of TRAPPIST-1, this means Kepler-186f orbits much closer to its star to achieve those just right temperatures, completing a full journey around its Sun in just 130 Earth days. But what sets it apart is its size. With a radius only about 10% larger than Earth's, the laws of physics strongly suggest it's a rocky world with a solid surface that could feature familiar landscapes of mountains, valleys, and perhaps even vast oceans. Scientists are particularly intrigued by the potential for a stable climate on this distant world. Its orbit at the outer edge of its system's habitable zone might mean it receives only about a third of the stellar energy from its sun that Earth gets from ours. This could lead to a cooler global climate, a scenario some researchers speculate might be similar to a perpetual Martian spring, or perhaps an early Earth-like environment before our own atmosphere thickened with life-giving gases. The planet's axial tilt is also believed to be very stable, which would prevent the wild, dramatic shifts in seasons that could make a world uninhabitable, offering a more consistent and potentially life-friendly environment over billions of years. The true legacy of Kepler 186f, however, extends far beyond its own potential. Its discovery was a monumental moment for planetary science because it told us one profoundly important thing: Earth-sized planets in habitable zones are not rare flukes. They exist. Our galaxy is likely filled with them. This single data point gave us the statistical confidence to believe that there could be tens of billions of potentially habitable, Earth-like worlds just within our Milky Way galaxy alone. It transformed the search for life from a question of if such planets existed to a question of where they are and what kind of life they might hold, forever changing the trajectory of astrobiology and fueling our hope that we might one day find a true second Earth among the stars. But for all the hope Kepler 186f inspired, it still orbited a very different kind of star than our own. The next world on our list, however, brings us even closer to a truly familiar cosmic setting. Located about 1,400 light-years away in the constellation Cygnus, we find Kepler 452b, a planet so reminiscent of our own that it's earned the nickname Earth's cousin. What sets this world apart is its parent star, a G-type yellow dwarf almost identical to our Sun in both size and temperature. For the first time, we weren't just looking at an Earth-sized planet in a habitable zone. We were looking at one orbiting a Sun-like star, a scenario that feels hauntingly familiar. This star, Kepler 452, is about 1.5 billion years older than our Sun. And because a planet forms at roughly the same time as its star, that makes Kepler 452b significantly older than Earth. Think about that for a moment. While life on our planet has had approximately 4 billion years to evolve from single-celled organisms to a civilization that can look out at the stars, this distant world has had an extra 60% more time, an additional 1.5 billion years, for its own story of life to unfold. That staggering head start is a profoundly compelling thought. If life did emerge there, what incredible forms might it have taken? Could a biosphere that has been thriving for 5.5 billion years have produced intelligence, technology, or complexities of biology we can scarcely imagine? The potential for a world that is not just living but truly ancient and advanced is one of the most captivating possibilities in the entire search for extraterrestrial life. Of course, this cousin isn't a perfect twin. Kepler 452b is classified as a super-Earth with a diameter about 60% larger than our planets. This increased size comes with significant implications. While it's likely to have a rocky surface, its gravity would be considerably stronger, roughly twice what we experience on Earth. This would create a world of dramatic, towering mountains and deep, vast canyons, as the powerful gravity would prevent peaks from reaching the heights of our Himalayas and cause the landscape to wear down differently. For any potential life, this environment would demand robust biological adaptations. Flora might be lower to the ground and incredibly sturdy, while fauna would likely be stockier and stronger to move under the increased weight. The planet's larger mass could also profoundly influence its geological activity and atmosphere. A more massive rocky planet is likely to have a hotter, more active interior, leading to prolonged and widespread volcanic activity. While this could continuously replenish the atmosphere with gases essential for life, it could also lead to more frequent mass extinctions, potentially resetting the evolutionary clock. Conversely, that strong gravity could help the planet hold onto a thick atmosphere, perhaps even denser than our own, which would offer superb protection from stellar radiation and help distribute heat evenly across the globe, potentially creating a stable, lush, planet-wide greenhouse perfect for life. The combination of a sun-like star, a stable orbit in the habitable zone for billions of years, and these unique planetary conditions makes Kepler 452b a prime candidate for a world that isn't just habitable, but truly inhabited. A place where the story of life has had more than enough time to write its most extraordinary chapters. While many of the worlds we visited so far orbit temperamental red dwarfs prone to violent flares, our next destination offers a far more stable and promising environment for life. Just 40 light-years away in the constellation Cetus, the Whale, lies a planet called LHS 1140b, and it might just be the most compelling candidate for habitability we've yet discovered. What makes this super-Earth so special is the star it calls home. Unlike the stormy Proxima Centauri, the red dwarf LHS 1140 is remarkably quiet and calm, a stable old star that provides its planetary family with a consistent and gentle flow of energy, dramatically increasing the chances that life could arise and thrive undisturbed on its most intriguing world. LHS 1140b itself is a heavyweight champion among rocky planets. Classified as a super-Earth, it's about 1.7 times the size of our own world, but boasts a mass nearly 7 times greater. This extraordinary density tells scientists that this isn't just a ball of rock. It's a planet likely dominated by a massive iron core, a world with incredible gravity and a structure that could profoundly influence its ability to host life. You might picture a landscape of immense, weighty mountains and deep metallic plains, a truly alien vista shaped by forces far more powerful than those on Earth. Crucially, this dense, massive planet orbits squarely within the heart of its star's habitable zone. The combination of its ideal location and its powerful gravity creates a scenario that has astronomers incredibly excited. LHS 1140b is an excellent candidate for possessing a thick, substantial atmosphere. A planet's gravity acts like an anchor, holding onto its gaseous envelope and preventing it from being stripped away by stellar winds. This world's strong pull means it could have successfully held onto a robust atmosphere for billions of years, a critical shield against radiation and a necessary blanket for regulating surface temperature and maintaining liquid water. This potential for a thick atmosphere, combined with the steady light of its tranquil star, makes LHS 1140b a premier target in the hunt for biosignatures. Its size and density make it an ideal laboratory for our most powerful telescopes. When it transits in front of its star, a larger percentage of the starlight is filtered through its atmosphere compared to a smaller, Earth-sized planet, giving instruments like the James Webb Space Telescope a clearer, stronger signal to analyze. Scientists will be looking for the telltale signs of a living world, not just the presence of water vapor, but potential combinations of gases like oxygen and methane that, when found together, are difficult to explain through geology alone and could point directly to biological processes. In the cosmic search for a second home among the stars, this dense, stable world orbiting its quiet sun represents one of our very best leads. Now, we journey 31 light-years from Earth to a system that demonstrates just how diverse and surprising these alien worlds can be. Orbiting a small, quiet red dwarf star known as JJ357 is a fascinating super-Earth called JJ357d. While its two sibling planets are roasted worlds far too hot for life, this third planet out finds itself in a far more comfortable position, sitting squarely within its star's habitable zone. It's a world that doesn't just hint at the possibility of water. It opens the door to a truly alien climate, one sculpted by a phenomenon we've encountered before: tidal locking. Because its star is so small and cool, GJ 357d must huddle close to stay warm, completing an orbit in just 55 Earth days. This intimate proximity almost certainly means one hemisphere is forever bathed in the faint, ruddy glow of its sun, while the other is plunged into eternal, frigid darkness. At first glance, this seems like a recipe for two extreme and uninhabitable environments: a scorching desert on the day side and a frozen wasteland on the night side. But the reality could be far more nuanced and promising. Climate models suggest that if this world possesses a sufficiently dense atmosphere, everything changes. A thick atmosphere acts as a planetary life support system, a massive heat transfer engine that could work to moderate these brutal temperature extremes. Winds could carry warmth from the perpetual day side over to the night side, preventing its atmosphere from freezing solid and collapsing onto the surface. Conversely, cooler air from the night side could flow back, tempering the intense heat under the constant starlight. This continuous circulation could create a thin, livable band of temperate conditions right along the terminator line, the twilight region where day meets night. But some scientists speculate an even more captivating scenario: a global ocean. If GJ 357d has a thick atmosphere and a significant amount of water, its entire day side might be covered by a vast, steaming water ocean, kept liquid by the constant energy from its star. The heat transported by atmospheric and oceanic currents could then prevent the night side from freezing completely, instead maintaining a lid of thick ice over a deep, dark subsurface ocean. This would create a world of stark contrasts: a hemisphere of warm, open sea under a hazy orange sky, and a hemisphere of icy crust hiding a cold, abyssal ocean below, with the potential for hydrothermal vents nurturing life in the perpetual dark, much like in the deepest trenches of our own oceans. The true nature of GJ 357d remains one of the most enticing puzzles in exoplanet science. Is it a barren, airless rock caught between two hellish extremes, or is it a dynamic water world, a planet with a global climate system unlike anything we see in our own solar system? Its location and mass make it a prime target for future telescopes, which will seek to analyze the chemical composition of its atmosphere and finally determine if this intriguing super-Earth is not just another planet but a potential home. Now we set our sights on a world that has sparked some of the most intense excitement and debate in modern astronomy: K2-18b. Imagine a planet not just with the potential for water, but one where we have already detected its vapor swirling high in the atmosphere. Located 120 light-years away in the constellation Leo, this discovery isn't just another exoplanet. It's a groundbreaking validation of our methods and a tantalizing hint at a completely new class of habitable worlds. K2-18b is what scientists call a mini-Neptune or a Hycean world, a term blending hydrogen and ocean. It's significantly larger than Earth, with a radius about 2.5 times greater and nearly 9 times more massive. This places it in a category between the rocky planets of our inner solar system and the gas giants like Neptune and Uranus. For a long time, astronomers assumed such worlds, with their thick, extended hydrogen-helium atmospheres and crushing pressures, would be utterly hostile to life as we know it. But K2-18b has completely upended that assumption, revealing a far more intriguing possibility. This massive planet orbits a cool, quiet red dwarf star squarely within its habitable zone. Because the star is so faint, the planet orbits very close, completing a year in just 33 Earth days. But the real stunner came when the Hubble Space Telescope analyzed the starlight filtering through K2-18b's atmosphere during its transit. The data revealed the unmistakable spectral signature of water vapor. This wasn't just an inference or a hopeful model. it was direct evidence of water in the atmosphere of a habitable zone exoplanet, a historic first that proved we can detect these crucial signs across the vast interstellar distances. The Hycean world hypothesis suggests that beneath this thick, hydrogen-rich atmosphere, there could lie a planet-wide ocean. Not a few lakes or seas, but a single, global, and incredibly deep ocean, possibly hundreds of kilometers deep, under a sky of immense pressure and perpetual hazy twilight. The conditions at the interface between this alien ocean and the watery atmosphere could be unlike anything on Earth, but the presence of liquid water, the universal solvent for life's chemistry, makes it a compelling environment to explore. Then came an even more astonishing and controversial claim. Follow-up observations with the immensely powerful James Webb Space Telescope tentatively detected traces of other molecules in the atmosphere, including carbon dioxide and methane. But the most electrifying potential find was a gas called dimethyl sulfide, or DSM. On Earth, DSM is almost exclusively produced by biological processes, specifically by phytoplankton in our oceans. There is no known non-biological geological process that creates it in significant quantities. If this detection is confirmed, it would represent the most compelling, if not definitive, hint of biological activity ever detected outside our solar system. Scientists are rightfully cautious, urging that the signal is faint and must be verified with further Webb observations. The planet's hydrogen-rich atmosphere itself could potentially be creating false positives or harboring unknown abiotic chemical pathways that might produce these gases. But the very possibility transforms K2-18b from a fascinating planetary oddity into perhaps the single most important target in the search for extraterrestrial life. It represents a test case for an entirely new concept of habitability, proving that the search for life cannot be limited to Earth twins. It forces us to broaden our imagination, to consider that biology might not just thrive on familiar rocky planets, but could also find a way in the vast, dark, high-pressure oceans of a water world shrouded in gas. Just a short cosmic hop from our own solar system, a mere 12 light-years away, we find one of the most intriguing and ancient stellar systems known to science, centered around a faint, fading ember of a star called Tidal star. This is an ultra-cool red dwarf, so small and dim it wasn't even discovered until 2003, despite being one of our closest neighbors. It's a stellar senior citizen, estimated to be at least 8 billion years old, nearly twice the age of our Sun. This incredible longevity sets the stage for its two remarkable planetary companions, Tidal star B and C, both rocky worlds with masses almost identical to Earth's, orbiting in the star's habitable zone and representing a profoundly different kind of opportunity for life. These two planets are not just nearby, they are among the most Earth-like worlds we have ever discovered in terms of pure mass, earning exceptionally high Earth Similarity Index scores. Tidal B, the inner planet, is the warmer of the two, with an equilibrium temperature that could allow for balmy, Earth-like conditions if it has a suitable atmosphere. Its sibling, Tidal C, orbits a bit farther out in what might be a cooler, more Mars-like environment. Both, however, fall within what astronomers call the optimistic habitable zone, meaning that under the right atmospheric conditions, either one could potentially support liquid water on its surface. Finding two such tantalizing targets around the same star so close to us makes this system a veritable treasure trove for planetary scientists. The most captivating aspect of this ancient system is the sheer expanse of time it has existed. Our solar system is 4.6 billion years old, and life on Earth took nearly 1 billion years to emerge. Tidal star and its planets have been around for roughly 8 billion years. That means life on either of these worlds has had an unimaginable head start, an extra 3 to 4 billion years of quiet, stable evolution compared to the story on our own planet. While Earth was still a molten ball of rock, these worlds could have already been cool, stable, and welcoming to the first stirrings of chemistry. If life did arise there, it has had more than twice the time we have had to diversify, complexify, and perhaps even intelligence to emerge and mature. Of course, they face the familiar challenges of red dwarf planets, likely being tidally locked to their faint sun. Yet, the remarkable age of this star works in their favor. While young red dwarfs are tempestuous and flare-prone, stellar activity calms dramatically with age. Teegarden's star is a placid, quiet elder, having long since settled into a stable and gentle rhythm, providing a consistent and non-lethal flow of energy to its planets for eons. This long-term stability is perhaps the single greatest asset for the development and persistence of life, offering a stable environment not for mere millions of years but for billions. The possibility that we are looking at two ancient, temperate, Earth-sized worlds, potentially harboring biospheres far older and more advanced than our own, makes the Teegarden star system one of the most compelling and humbling destinations on our list. Now we turn our attention to a system that has offered a particularly clean and promising signal in the search for Earth-like worlds, a planet discovered by NASA, a transiting exoplanet survey satellite or TESS. Just over 100 light-years away in the constellation Dorado, we find TOI 700d. What makes this world so special isn't just its size or location, but the remarkable character of the star it orbits, a quiet, well-behaved M-dwarf star that shows very little of the violent flaring activity that plagues so many other red dwarf systems. This stellar stability gives TOI 700d a significant advantage in the potential habitability stakes from the very start. This Earth-sized planet is the outermost of 3 known worlds in its system, orbiting comfortably within the star's conservative habitable zone. A year here lasts 37 Earth days, a rapid orbit that is only possible because the star is so small and cool. But unlike many planets in similar tight orbits, TOI 700d is not believed to be tidally locked. Its orbit might be in a spin-orbit resonance, a gravitational dance where the planet rotates on its axis 3 times for every 2 trips around its star. This means the entire surface of the planet would experience both day and night, cycling through a regular rhythm of sunlight and darkness. This is a crucial distinction, as it would prevent the development of those extreme permanent day and night sides, instead promoting a more even distribution of heat and a much more Earth-like global climate system. Climate scientists have run sophisticated models on this world, and the results are incredibly encouraging. If TOI 700d has an Earth-like atmosphere rich in nitrogen and carbon dioxide with a surface pressure similar to our own, the models suggest it could easily maintain a temperate climate with vast regions where the average temperature is well above the freezing point of water. One particularly compelling simulation even predicted that a large portion of the planet's dayside could be covered by a massive, deep ocean, with land masses concentrated on the cooler night side and around the terminator region. This would create a world of stunning contrasts, a bright, cloud-swept oceanic hemisphere and a darker, possibly icy continental hemisphere. The presence of water clouds, just like those on Earth, appears to be a key ingredient in these optimistic models. Clouds are not just for rain, they play a critical role in regulating a planet's temperature by reflecting a portion of the incoming stellar radiation back into space, preventing a runaway greenhouse effect. The models indicate that with this cloud feedback, TOI 700d could maintain a stable, warm climate perfect for liquid water, even though it receives 86% of the stellar energy that Earth gets from the Sun. This combination of factors, its Earth-like size, its stable and quiet star, its potential for a day-night cycle, and the strong climate model predictions for surface water, makes TOI 700d one of the most credible and exciting candidates for a truly habitable world we have yet found. It stands as a powerful testament to the idea that not all red dwarf planets are hostile, and that some might offer environments startlingly similar to our own. Imagine a sky not with one sun but with 3. This isn't a scene from a science fiction novel. It's the daily reality for a remarkable super-Earth known as JJ667cc, located a mere 22 light-years from Earth in the constellation Scorpius. This world is part of a truly unique stellar arrangement, a triple-star system. The planet itself orbits the smallest star of the trio, a red dwarf designated JJ667c. The other two stars, a pair of K-type orange dwarfs, orbit each other much farther out, appearing in JJ667cc's sky not as blazing suns, but as a pair of brilliantly luminous stars, casting a perpetual, soft twilight that would make its nights anything but dark. Despite this complex celestial dance, JJ667cc finds itself in an enviable position, nestled firmly in the center of its primary star's habitable zone. It completes an orbit around its dim red sun in just 28 Earth days, but receives almost exactly the same amount of stellar energy from it that Earth gets from our sun. This remarkable coincidence makes it one of the most Earth-like worlds we've discovered in terms of energy balance, a key ingredient for maintaining a climate that could support liquid water. The presence of the distant binary stars doesn't significantly heat the planet, but they do contribute a gentle, constant glow, ensuring the surface is never in total darkness. The planet is classified as a super-Earth with a mass at least 4 times that of our own world. This strongly suggests a rocky composition, a place with a solid surface where oceans could pool and continents could rise. However, that greater mass comes with consequences. The surface gravity would be significantly stronger, likely around 60% higher than what we experience. This would create a world of lower, more weathered mountain ranges and profoundly deep ocean trenches. Any potential life would need to be robust, adapted to thrive under a much heavier weight, perhaps leading to sturdier, more dense biological structures. The true wonder of JJ667cc lies in the possibility of its climate. One might assume a planet with 3 suns would be subject to chaotic and extreme temperature swings, but the reality could be surprisingly stable. Because the 2 additional stars are so distant, their warming effect is minimal. The primary driver of the climate remains the steady, close orbit around its red dwarf sun. Advanced climate models indicate that if JJ667cc possesses an Earth-like atmosphere, it could easily maintain global average temperatures very similar to our own. The gentle, additional light from its companion stars would simply act as a constant, subtle background illumination, potentially even helping to moderate the climate by preventing the night side from cooling down too drastically. This combination of factors, a sun-like energy input, a likely rocky surface, and the potential for a stable atmosphere elevates JJ667cc to the status of a top-tier candidate in the search for life. It proves that habitable worlds are not limited to simple, single-star systems like our own, but can thrive in more complex stellar environments as well. It expands our definition of a habitable zone and fuels the hope that life, in its relentless drive, could find a way even under the soft, multiple lights of a triple sunset. Venturing deeper into the legacy of the Kepler telescope, we arrive at a system that gifted us not 1, but 2 potential water worlds, each offering a starkly different vision of what a habitable planet might look like. Roughly 1,200 light-years away in the constellation Lyra, the star Kepler-62 is home to a family of 5 known planets. 2 of its outermost members, Kepler-62e and Kepler-62f, are both super-Earths orbiting within the habitable zone, presenting us with a fascinating comparative study of how size and orbital distance can sculpt 2 wildly different environments around the same star. First, let's meet Kepler-62e, the inner and warmer of the pair. This world is about 60% larger than Earth and completes a full orbit around its K-type orange dwarf star in just 122 days. Its position closer to the star suggests it likely receives a significantly greater amount of stellar energy than Earth does from our Sun. This has led many planetary scientists to classify it as a possible ocean planet or even a water world. The thinking is that its larger size and stronger gravity would allow it to hold onto a much thicker atmosphere than Earth, potentially rich in water vapor and other greenhouse gases. This dense atmospheric blanket, combined with the increased energy input, could create a powerful greenhouse effect, warming the entire surface to the point where any water present would exist as a planet-wide global ocean, potentially tens or even hundreds of kilometers deep. There might be no land masses at all, just an endless, steaming sea under a thick, cloudy sky, with conditions reminiscent of a prehistoric Earth, but on a far grander and more alien scale. Its sibling, Kepler-62f, tells a different story. Slightly smaller at about 40% larger than Earth, it orbits farther out, taking 267 days to circle its sun. At this greater distance, it receives much less warmth, placing it on the cooler outer edge of the habitable zone. The most likely scenario for this world is that of an icy super-Earth. If it has a thin atmosphere, its surface water could be largely frozen, a global ice sheet resembling a snowball Earth. However, a more intriguing and hopeful possibility exists. If Kepler-62f has a sufficiently dense atmosphere rich in greenhouse gases like carbon dioxide, it could maintain a temperate climate through a strong greenhouse effect, preventing its water from freezing solid. Even more compelling is the prospect that it could mirror the environments we see on moons like Europa or Enceladus in our own solar system. Beneath a thick, icy crust, a vast global subsurface ocean could be churning, kept liquid not by starlight, but by the internal heat generated from radioactive decay in its core or from the gravitational tug of war with its sibling planets. This would be a world where life, if it exists, would thrive not under an open sky, but in the perpetual darkness of a deep ocean abyss, potentially around hydrothermal vents on the ocean floor. What makes the Kepler-62 system so profoundly important is this direct comparison. Here, around a single star, we have two prime examples of how the concept of habitability is not a one-size-fits-all proposition. It's a spectrum. Kepler-62e represents the warm, maybe even tropical, end of that spectrum, a world where the entire surface could be a single, dynamic marine environment. Kepler-62f represents the cold, cryptic end, a world where life's potential is locked away beneath a shell of ice, hidden from direct view but perhaps no less vibrant. Together, they dramatically expand our understanding of where life could take root, pushing us to consider that the most common abodes for life in our galaxy might not be pale blue dots like Earth, but rather steamy water worlds or icy satellites harboring secret oceans. They are a powerful reminder that life is tenacious and adaptable, and that the environments it can call home are far more diverse and extraordinary than we once ever dreamed. Now, we travel to one of our very closest known planetary neighbors, a world so near that it sparks the imagination with the possibility of one day being our first stop on an interstellar journey. Just 14 light-years away, practically next door on the cosmic scale, orbits the super-Earth known as Wolf 1061c. This places it within the same stellar vicinity as Proxima Centauri, making it one of the most accessible and tantalizing targets for future study. It's a reminder that the search for life isn't always about peering into the deepest reaches of the galaxy. Sometimes the most compelling answers might be waiting for us just around the corner. Wolf 1061c is part of a compact three-planet system orbiting a stable M-type red dwarf star. The planet itself is a substantial world with a mass about 4 times that of Earth, firmly placing it in the super-Earth category and strongly suggesting a rocky composition. Its most critical feature is its orbit, which places it squarely within its star's calculated habitable zone. However, its position there is a delicate and precarious one, sitting extremely close to the inner edge of that zone. This proximity to its star is a double-edged sword, creating a razor-thin margin between a world that is habitable and one that is a scorching hellscape. This precarious balance evokes a powerful and cautionary example from our own solar system, Venus. Like Wolf 1061c, Venus orbits near the inner boundary of our Sun's habitable zone. Billions of years ago, it may have even had oceans, but a runaway greenhouse effect took hold. The planet's thick atmosphere, rich in carbon dioxide, trapped more and more solar energy, causing surface temperatures to soar to levels that melt lead and boiling away any chance for liquid water. Wolf 1061c could be a cosmic cousin to Venus, a world where a similar process unfolded. If its atmosphere is too thick or contains too many greenhouse gases, it could be locked in a permanent state of extreme heat, its surface a barren, volcanic landscape under a crushing, toxic sky. Yet, there is a flip side to this story, a scenario where this very same location could be its greatest asset. A planet's climate is not dictated by orbit alone. Its atmosphere is the ultimate regulator. If Wolf 1061c has an atmosphere with the right composition and density, perhaps one with reflective cloud cover or a lower concentration of greenhouse gases, it could effectively counterbalance the intense stellar energy it receives. This atmosphere could act as a global thermostat, distributing heat efficiently and maintaining surface temperatures that would allow water to remain in its liquid state. Its larger mass might actually aid in this, providing the strong gravity needed to hold onto a protective atmospheric blanket for billions of years. The potential for tidal locking adds another layer of complexity to its climate puzzle. If one side of the planet permanently faces its star, we could see a world of dramatic extremes. But as with other such planets, a substantial atmosphere could work to moderate these temperatures, creating a narrow, temperate ring at the twilight terminator where conditions might be surprisingly comfortable. The possibility exists that Wolf 1061c is not a Venus-like inferno, but a dynamic and diverse world with its own unique and stable climate system, a place where life found a way to thrive in the balance between fire and ice. Its incredible proximity makes it a prime candidate for the next generation of telescopes, which will aim to analyze its atmosphere and finally answer the question of whether this nearby neighbor is a warning or a welcome. Journeying over 2,700 light-years into the depths of the constellation Cygnus, we encounter another testament to the Kepler telescope's incredible legacy, a world that stands as one of the mission's most significant and promising discoveries. Kepler 1638b is a planet that captivates scientists not for its extreme or alien nature, but for its profound sense of familiarity. In a catalogue filled with thousands of exotic worlds, this one shines for how closely it echoes the basic parameters of our own home, representing one of the most compelling Earth analogues ever identified in the vast cosmic ocean. What sets Kepler 1638b apart from many other habitable zone candidates is the star it calls home. Unlike the red dwarfs that dominate our list, this planet orbits a G-type yellow dwarf star, a stellar classification that includes our own Sun. This star, Kepler 1638, is remarkably similar to ours in both size and temperature, creating a stellar environment that feels instantly recognizable. For a planet to be in the habitable zone around a Sun-like star, it must orbit at a distance much farther than the close-in worlds around dim red dwarfs. A year on Kepler 1638b lasts 259 Earth days, placing its orbital distance and period in a range that feels far more analogous to the rhythms of our own solar system, reducing the risks associated with tidal locking and intense stellar flares. The planet itself is a near-perfect match for Earth in terms of size, with a radius only about 6% larger. This small difference is critically important, It strongly indicates a rocky composition with a solid surface where landscapes of mountains, valleys, and most importantly, ocean basins could potentially exist. Its placement within the habitable zone is not on the extreme fringes but in a more stable, central location, suggesting it receives a level of stellar energy that could comfortably maintain liquid water, provided it has the right atmospheric conditions. And that is the great, lingering question that makes this world such a priority for astronomers. Does it have an atmosphere? A planet's atmosphere is its life support system, its temperature regulator, and its shield against harmful radiation. For a world like Kepler 1638b, its Earth-like size presents both a challenge and an opportunity. A smaller planet has weaker gravity, which can make it more difficult to hold onto a thick atmospheric blanket over billions of years, especially if its star has an active youth. However, its Sun-like star is far less volatile than a red dwarf, offering a more stable and gentle radiation environment that is less likely to strip away a protective gaseous envelope. This is where the next generation of observatories, most notably the James Webb Space Telescope, enters the story. The immense distance to Kepler 1638b makes detailed atmospheric study extraordinarily difficult, pushing our technological capabilities to their absolute limit. But the scientific payoff would be monumental. By analyzing the starlight that filters through the planet's atmosphere during its transit, Webb could hunt for the chemical fingerprints of key molecules like water vapor, carbon dioxide, methane, or even oxygen. Detecting a combination of these gases could point toward geological activity or something far more exciting, a living, breathing biosphere. Kepler 1638b represents a quiet, patient hope in the search for life, a world that doesn't rely on exotic hypotheses or extreme environments, but on the simple, powerful idea that a planet almost exactly like ours, orbiting a star almost exactly like our Sun, might just have followed a similar, miraculous path. Now, let's shift our gaze to a star that offers a gentler, more stable kind of light for any potential life. 42 light-years away in the constellation Pictor, we find HD 40307G, a super-Earth that presents a compelling alternative to the volatile environments of many red dwarf planets. What makes this world so intriguing is its parent star, a K-type orange dwarf. These stars are a perfect middle ground. They are smaller, cooler, and longer-lived than our Sun, but significantly larger, warmer, and most importantly, much calmer than the flaring M-dwarf red dwarfs that dominate our list of habitable worlds. This stellar serenity offers HD 40307G a far more stable and less hostile radiation environment, dramatically boosting its prospects as a viable abode for life. The planet itself is a substantial world with a mass at least 7 times greater than Earth's. This classifies it firmly as a super-Earth, but its location is what truly captivates astronomers. HD 40307G is the outermost of 6 planets discovered in this system, orbiting squarely within the star's habitable zone. A year here lasts just under 200 Earth days, a period that feels far more familiar compared to the breakneck orbits of weeks or days seen around smaller stars. This greater orbital distance immediately reduces the risk of the planet being tidally locked, freeing it from the fate of a permanent day side and a permanent night side. This potential for a normal rotation is one of the most exciting aspects of HD 40307G. Early analyses of the system's dynamics suggest this planet could very well be spinning on its axis in a way that creates a regular day-night cycle, much like the one we experience on Earth. This is a critical ingredient for habitability that is often missing from other candidates. A rotating planet allows for the even distribution of stellar heat across its surface, preventing the brutal temperature extremes of a tidally locked world. This, in turn, is the fundamental engine that drives a stable and complex climate system. Imagine the weather patterns that could emerge on such a world. With a day-night cycle and a likely rocky surface, HD 40307G could experience familiar atmospheric phenomena. Winds that shift with the rising and setting of its orange sun, cloud formations that travel across its skies, and precipitation that falls to nourish the land. Its stronger gravity would certainly influence these patterns, potentially creating a thicker atmosphere with higher air pressure and more dramatic weather systems, but the underlying rhythm would be reassuringly Earth-like. This isn't a world of eternal twilight or scorching deserts. It's a planet that could have seasons, weather fronts, and a dynamic environment where life wouldn't have to cling to survival in a single narrow band, but could potentially flourish across the entire globe. The combination of a quiet K-type star, a secure position in the habitable zone, and the potential for a rotating world with a balanced climate makes HD 40307G a standout candidate. It represents a different and perhaps more optimistic path for planetary habitability, one that doesn't require life to adapt to the fury of a red dwarf, but instead allows it to evolve under the steady, gentle gaze of a reliable orange sun. While many red dwarf stars are chaotic and unpredictable, our next destination orbits one of the quietest and most stable stellar hosts we've ever found. Just 11 light-years away, a stone's throw in interstellar terms, lies Ross 128b, a temperate world offering a far more peaceful existence than many of its volatile counterparts. Its parent star, Ross 128, is an old, inactive M-dwarf that has long since settled into a calm and gentle rhythm, having shed the violent flaring tantrums of its youth. This stellar serenity is the planet's greatest advantage, providing a stable and consistent flow of energy, and most crucially, posing a dramatically reduced threat of sterilizing radiation bursts that could strip away atmospheres or scald surfaces clean of any emerging biology. What truly captivates astronomers about this world is its remarkable potential for Earth-like conditions. Ross 128b has a mass very similar to our own planet, making it one of the most likely rocky terrestrial worlds we've discovered so close to us. It orbits its placid star every 10 days, a tight loop that places it well within the calculated habitable zone. While that might sound scorchingly close, remember that Ross 128 is far cooler and dimmer than our Sun. This proximity is precisely what allows the planet to achieve a potential Goldilocks temperature. Early climate models suggest that, with a sufficiently thick atmosphere, Ross 128b could easily maintain average surface temperatures that would allow for pools, lakes, or even vast oceans of liquid water to exist. The possibility of a substantial atmosphere is where this world's calm star becomes a game changer. A planet's ability to hold onto its gaseous envelope over billions of years is a constant battle against the erosive power of its star. Young, active red dwarfs blast their planets with intense ultraviolet and X-ray radiation, which can literally boil away an atmosphere over time. But Ross 128's advanced age and quiescent nature mean it emits very little of this damaging radiation. This gives Ross 128b an unparalleled opportunity to retain a robust and protective atmospheric blanket, one that could effectively distribute heat around the globe and shield the surface from the lower-level stellar particles that do get through. This combination of factors, a rocky composition, an ideal energy balance, and a high probability of a stable atmosphere, makes Ross 128b not just a candidate for habitability, but one of the very best we have found. It stands as a quiet, hopeful beacon, a nearby world that may have enjoyed the billions of years of peace and stability necessary for life's delicate chemistry to begin and to flourish. Now we set our sights on a world that masterfully illustrates the delicate balance of planetary climates, a super-Earth known as Kepler 1229b. Discovered by the Kepler telescope roughly 770 light-years away in the constellation Cygnus, this planet presents a fascinating counterpoint to the warmer, more tropical candidates we've explored. It orbits a red dwarf star, but its story is not one of blistering heat or tidal locking extremes. Instead, it offers a vision of a world where habitability might be found in the cool, quiet margins of possibility. What makes Kepler 1229b so intriguing is its specific placement within its star's habitable zone. While many planets we've discussed orbit closer to the inner, warmer edge, this world is situated much farther out on the cooler, outer boundary of that life-giving region. As a result, the amount of stellar energy it receives from its faint sun is calculated to be remarkably similar to the amount of energy that Mars gets from our Sun. At first glance, this comparison might seem discouraging. Mars is a frozen, arid desert, its surface water long gone and its atmosphere too thin to retain heat. This would suggest that Kepler 1229b is a profoundly cold world, a snowball where any surface water should be permanently locked away as ice. But this is where the critical ingredient of atmosphere changes everything. A planet's surface temperature is not dictated by starlight alone. It is primarily governed by the insulating blanket of gases that surrounds it. Mars is frigid because it lost its thick atmosphere long ago. Kepler 1229b, however, is a super-Earth with a mass about 3 times greater than our own planet. This greater mass grants it a powerful gravitational grip, making it far more capable of holding onto a dense, substantial atmosphere over billions of years. If this world has managed to retain a thick atmosphere rich in greenhouse gases like carbon dioxide or methane, the entire equation flips. Such an atmosphere would act as a planetary-scale heating system, trapping the meager stellar energy it receives and distributing it across the globe through winds and ocean currents. This greenhouse effect could raise average surface temperatures well above the freezing point of water, transforming a potential ice ball into a temperate, albeit cool, world. We see a small-scale version of this principle in our own solar system with Saturn's moon Titan, which has a thick atmosphere that keeps its surface much warmer than it would be otherwise, despite receiving only a tiny fraction of the Sun's energy that Earth does. This opens up 2 compelling and equally fascinating scenarios for what Kepler 1229b might be like. In the first, it could be a world with a climate reminiscent of a cool autumn day on Earth, global in scope. Vast oceans might persist on its surface, their waters dark and deep, perhaps shrouded under a perpetual layer of water clouds. Life here would have adapted to lower light levels and cooler temperatures, but could otherwise thrive in a familiar marine environment. The second, and perhaps more likely, scenario is even more alien and captivating. If the greenhouse effect isn't quite strong enough to warm the entire surface, liquid water might not be found in open oceans, but could instead exist in vast subterranean reservoirs deep beneath a global ice sheet. This would make Kepler 1229b less like Earth and more like Jupiter's moon Europa, a world with a frozen crust hiding a global ocean below. On such a planet, life would not bask under an open sky, but would be confined to the dark, abyssal depths, potentially thriving around geothermal vents on the ocean floor, drawing energy from the planet's internal heat rather than from the faint light of its distant sun. This hidden biosphere could be just as rich and complex as any on the surface, completely isolated from the cold, silent world above. Kepler 1229b stands as a powerful lesson that a planet potential is not written solely by its distance from its star, but by the complex and dynamic interplay between that starlight and the atmospheric and geological forces that shape its environment from within. Our exploration now takes us to a nearby system that offers a fascinating 2-for-1 deal in the search for alien environments, showcasing how 2 wildly different worlds can emerge from the same stellar nursery. Just over 17 light-years away, a small, quiet red dwarf star known as JJ 3323 hosts a pair of super-Earths, JJ 3323b and c. These two planets present a stark study in contrasts, demonstrating the razor-thin line that often separates a scorching wasteland from a potentially life-giving oasis. The inner planet, JJ 3323b, is a world of fire and extremes. It whips around its star in a blistering 5-day orbit, so close that its surface is almost certainly baked at temperatures that would vaporize rock. This is a super-Earth in the most literal sense, a rocky world larger than our own, but one where any notion of habitability has been utterly erased by its searing proximity to its sun. It serves as a powerful reminder of the brutal conditions that exist just a short orbital distance from the precious habitable zone. Its sibling, JJ 3323c, tells a far more hopeful and complex story. Orbiting farther out, this planet completes a journey around its star every 40 days, a trajectory that places it squarely within the system's calculated habitable zone. Its location suggests it receives a similar amount of stellar energy as Earth does from our Sun, a promising start for any world with dreams of hosting liquid water. Yet its ultimate fate hinges almost entirely on a single critical factor that we cannot yet see: the history and composition of its atmosphere. This world stands at a cosmic crossroads, presenting two equally plausible but dramatically different destinies. In one scenario, JJ 3323c could have followed a path eerily similar to that of Venus in our own solar system. If its atmosphere became too thick with greenhouse gases like carbon dioxide early in its history, it could have triggered a runaway greenhouse effect. The planet's oceans would have boiled away, its surface would have heated to infernal temperatures, and it would now be a permanently scorched and hostile desert, a tragic twin to its already hellish inner sibling. But there is another, far more inviting possibility. If JJ 3323c managed to develop and maintain an atmosphere with a more moderate composition, one that could effectively regulate temperature without spiraling out of control, it could be a perfectly temperate world. Its larger mass as a super-Earth would give it the gravity needed to hold onto this protective blanket of gas for billions of years. This atmosphere could distribute the star's heat efficiently, potentially creating a global climate with vast regions where liquid water could pool on the surface. The presence of its volatile inner neighbor, Planet B, adds another layer of intrigue, as its gravitational influence could have affected the delivery of water and other volatile compounds to JJ 3323c during the system's formation, either enriching it as a water world or leaving it a dry, barren rock. This profound uncertainty is precisely what makes this system, and JJ 3323c in particular, one of the most compelling targets for the next generation of astronomy. The star is nearby and quiet, and the planet's orbit is aligned such that it passes in front of its star from our viewpoint. This gives us a golden opportunity to point our most powerful telescopes, like the James Webb Space Telescope, toward it and perform atmospheric spectroscopy. By dissecting the starlight that filters through the planet's atmosphere during these transits, we can hunt for the chemical fingerprints of its gases. Finding signs of water vapor would be a monumental discovery, but the real jackpot would be detecting the specific cocktail of gases that could tell us whether this world is a Venus-like cautionary tale or a temperate, Earth-like haven. JJ 3323c is a planetary mystery waiting to be solved, a nearby key to understanding how common or rare our own world's comfortable climate might be across the galaxy. Now we travel to one of the most ancient and storied worlds ever discovered, a planet that feels less like a distant neighbor and more like a living relic from the dawn of the cosmos itself. Located just 13 light-years away, Kapteyn b is a super-Earth orbiting a star that is fundamentally out of place. Kapteyn's star is a halo star, a solitary wanderer that does not orbit within the main disk of our Milky Way galaxy like our Sun does. Instead, it traces a long, looping, elliptical path high above and below the galactic plane, a trajectory that tells astronomers it was likely born elsewhere, perhaps in a small dwarf galaxy that was devoured and torn apart by the Milky Way in a colossal act of galactic cannibalism billions of years ago. This extraordinary origin story gives Kapteyn star and its planet an almost unimaginable age. Current estimates place this system at around 11 billion years old. To grasp the sheer scale of that time, consider this. Our universe itself is only about 13.8 billion years old. Our solar system, by comparison, is a youthful 4.6 billion years old. Kapteyn b has been around for more than twice as long. When this planet was already over 6 billion years old, our Earth was still a cloud of gas and dust waiting to be born. This incredible seniority is the single most compelling aspect of this world, because it means that life on Kapteyn b, if it ever emerged, has had an absolutely enormous head start. While life on Earth has had roughly 4 billion years to evolve from the first single-celled organisms to a spacefaring civilization, any biology on Kapteyn b would have had over twice that time, an extra 7 billion years, to develop, complexify, and perhaps achieve wonders of intelligence and technology we can scarcely comprehend. The planet itself orbits within the habitable zone of its cool, dim red dwarf star. It's a substantial world with a mass at least 5 times that of Earth, suggesting a rocky composition with a solid surface and gravity more than twice as strong as what we experience. Its 48-day orbit provides it with a level of stellar energy that could, in theory, support liquid water, assuming it has the right atmospheric conditions. But life here would face significant challenges rooted in its star's nature. Red dwarfs are known for their volatility, and while Kapteyn star is now relatively quiet, its long history is unknown. Furthermore, its dimness means the planet receives far less visible light than Earth, bathing any potential landscape in a perpetual, dim reddish glow. Photosynthetic life, if it exists, would have had to adapt to this faint light, perhaps evolving to use different wavelengths of the spectrum entirely. Yet, the most thrilling possibility of Kapteyn b lies in that profound age. Imagine a biosphere that has been evolving and adapting for 11 billion years. The diversity of life could be staggering, with forms and functions so alien they defy our Earth-centric imagination. Evolution on such a timescale might have produced organisms with incredible biological redundancies, near immortality, or forms of intelligence and communication utterly different from our own. This world forces us to ask not just if life exists out there, but what life becomes when it is given almost the entire age of the universe to write its own story. Kapteyn b isn't just a candidate for habitability. It is a portal to a deeper cosmic past, a chance to find evidence that life is not a late blooming novelty in the universe, but a fundamental force that may have arisen when the cosmos itself was still in its relative infancy. Returning to the incredible TRAPPIST-1 system, we now shift our focus from the temperate promise of planet E to its intriguing sibling, TRAPPIST-1f. This world offers a completely different vision of what habitability might look like, moving from a potentially Earth-like environment to one that is profoundly, fascinatingly alien. While both planets orbit within the star's habitable zone, TRAPPIST-1f resides on its cooler outer edge, receiving significantly less stellar warmth. Its orbit takes just 9.2 Earth days, a frantic pace dictated by the need to stay warm enough around its faint red sun, and this position paints a picture of a world where surface water, if it exists at all, is likely frozen solid. In terms of its physical characteristics, TRAPPIST-1f is remarkably similar to Earth in both size and mass, though it is just a touch less dense. This near-identical profile strongly suggests a rocky composition, a world with a solid surface you could theoretically stand on. But you would not find a familiar landscape. The reduced energy input from its star means the most probable scenario for this world is that of a global ice ball. Its surface would likely be a vast, cratered plain of water ice, stretching out under a dim, deep orange sky, with temperatures that would make Antarctica feel balmy. At first glance, this seems to rule out the possibility of life, as biology as we know it requires liquid water. However, this is where the most thrilling possibility emerges, one inspired by discoveries right here in our own solar system. TRAPPIST-1F could be what scientists call an eyeball planet, but with a twist. While one side may permanently face its star due to tidal locking, the feeble warmth might not be enough to melt a central surface ocean. Instead, the true potential for life lies hidden from view, deep beneath the frozen crust. The planet's Earth-like mass and likely rocky interior generate something crucial: internal heat. Radioactive decay in its core, combined with the gravitational squeezing from its star and 6 sibling planets, could provide enough energy to maintain a vast, global liquid water ocean trapped between the icy surface and the rocky seafloor below. This would make TRAPPIST-1F a direct cosmic cousin to moons like Jupiter's Europa or Saturn's Enceladus, but on a planetary scale. Imagine a world where the entire surface is a silent, frozen desert, but just a dozen kilometers below your feet lies a dark, abyssal ocean that could be dozens or even hundreds of kilometers deep, a hidden sea containing more liquid water than all of Earth's oceans combined. In this perpetual darkness, life would not rely on sunlight for energy but on chemistry. Hydrothermal vents on the ocean floor, much like those found in Earth's deepest trenches, could spew mineral-rich fluids into the water, providing the energy and building blocks for entire ecosystems to thrive completely independent of the star above. Strange, blind creatures could navigate these pressurized waters, and microbial life could form the base of a food web that has never known a sunrise. TRAPPIST-1F challenges our Earth-centric view of habitable worlds, suggesting that some of the most common abodes for life in our galaxy might not be pale blue dots with surface oceans, but frozen white marbles guarding their life-giving secrets deep within. And now we arrive at one of the most promising and recently discovered gems in the exoplanet catalog, a world that almost seems tailor-made for our most powerful observatories. 100 light-years away, orbiting a faint star in the constellation Eridanus, is LP-899c, a super-Earth that has astronomers buzzing with anticipation. It was discovered by an incredibly aptly named Project Speculus, which stands for Search for Habitable Planets Eclipsing ULTRA-C stars. Just as the sweet treat is known for revealing a delicious center, this project is designed to find worlds that eclipse their dim stars, revealing their own potentially sweet spots for habitability. This planet is a substantial world, about 40% larger than Earth with a mass more than 7 times greater, placing it firmly in the super-Earth category and strongly suggesting a rocky composition with a solid surface. But its most captivating feature is its orbit around an ultra-cool red dwarf star, a class of star even smaller and cooler than the typical M-dwarfs we've discussed. These stellar embers are so faint that their habitable zones are incredibly close in. LP-899c completes a full journey around its sun in just 8.4 Earth days, a year that flashes by in less than a week. Despite this intimate dance, the planet receives just slightly more stellar energy than Earth does from our sun, placing it squarely in the middle of its star's habitable zone and making it one of the best-positioned worlds we know of for potential surface water. What truly sets this world apart and why it has rocketed to the top of observation lists is a perfect storm of favorable conditions for atmospheric study. First, its star is exceptionally quiet and stable, even for an ultra-cool dwarf. It shows very little of the violent flaring activity that plagues stars like Proxima Centauri, meaning any atmosphere this planet has would have faced a much gentler cosmic environment, giving it a far better chance of surviving for billions of years. Second, the planet is an ideal size for investigation, large enough that its atmosphere presents a bigger, clearer target for our telescopes to analyze, but not so large that it's likely to be a gaseous mini-Neptune without a surface. Most importantly, from our vantage point, this world transits directly in front of its star. Each time it does, a fraction of the star's light filters through the planet's atmosphere, allowing instruments like the James Webb Space Telescope to perform a technique called transmission spectroscopy. By breaking that filtered starlight into a spectrum, scientists can read the unique chemical fingerprints of the gases present. LP-899c is considered one of the very best targets in the entire sky for this delicate work because its star is so small and dim. When the planet transits, it blocks a larger percentage of the star's light compared to a transit around a sun-like star, creating a stronger, clearer signal. It's like trying to detect the subtle tint of a sunglasses lens by holding it up in front of a faint light bulb versus a brilliant searchlight. The dimmer source makes the subtle effect much easier to see. The scientific community is poised to direct Webb's formidable gaze toward this world, hoping to detect the telltale signs of water vapor, carbon dioxide, methane, or even the tantalizing potential biosignature of oxygen. Finding a thick, water-rich atmosphere around LP-899c would be a monumental discovery, suggesting that even these tiny, cool stars can host worlds with familiar, life-friendly conditions. It represents the thrilling next phase of exoplanet science, moving beyond mere discovery and into the era of true characterization, where we can begin to understand the climate and chemistry of our most promising neighbors in the galaxy. Leaving behind the ultra-cool dwarfs, we venture deeper into the Kepler telescope's treasure trove to a world that serves as a powerful reminder of Earth's own delicate balance. Approximately 820 light-years from us in the constellation Cygnus orbits Kepler 1652b. This planet stands out not for extreme size or exotic stellar hosts, but for its profound sense of familiarity. It's one of the precious few exoplanets we've found that is almost a perfect match for Earth in terms of size, with a radius estimated to be just 1.1 times that of our own world. This near-identical scale strongly suggests a rocky composition, a place with a solid surface where familiar geological processes could shape continents and ocean basins, making it one of the most compelling Earth analogues in the entire catalog. This Earth-sized world orbits a red dwarf star, a class we've become very familiar with, but its specific orbital characteristics are what make it so intriguing. Kepler 1652b completes a full journey around its sun in just over 38 Earth days. While that sounds incredibly fast, it's a necessity to stay warm around such a small, cool star. The remarkable fact is that despite this tight orbit, the amount of stellar energy the planet receives from its faint sun is calculated to be almost exactly the same as the amount Earth gets from our sun. This coincidence is a cornerstone of its potential habitability. It means that, in theory, the energy available to power a climate system and maintain liquid water is virtually identical to what we have here at home. This energy balance is a critical starting point, but it's only the beginning of the story. The true potential of any world hinges on its ability to translate that stellar energy into a stable, global climate, and this is where the mysteries and challenges for Kepler 1652b begin. Like many planets orbiting red dwarfs, it is likely tidally locked, with one hemisphere perpetually bathed in faint, ruddy light and the other shrouded in endless night. Without an atmosphere, this would create two brutally extreme and uninhabitable environments. However, climate scientists are actively creating sophisticated models to understand how an atmosphere could completely reshape this destiny. If Kepler 1652b has managed to hold onto a substantial atmospheric envelope, that gas becomes a planetary life support system. Winds and ocean currents would act as a massive heat transfer engine, circulating warmth from the day side to the night side and preventing the atmosphere from freezing solid. This could create a continuous band of temperate conditions around the entire planet, particularly along the twilight terminator line, or it could even moderate the entire globe into a surprisingly stable climate. Ongoing research is focused on trying to pinpoint what kind of atmosphere would be needed to achieve this stability. The composition and thickness of that gaseous blanket are everything. A thin atmosphere would lead to a frozen, Mars-like world. A too thick atmosphere rich in greenhouse gases like carbon dioxide could trigger a runaway greenhouse effect, boiling away any oceans and turning the planet into a Venus-like inferno. But if the atmosphere has the right balance, perhaps a nitrogen-dominated sky with the perfect amount of carbon dioxide and water vapor to create a moderate greenhouse effect, then Kepler 1652b could be a world of stunning beauty. Its permanent dayside might feature a vast, open ocean under a hazy orange sky, while the night side could be a dark, frozen continent, with the sliver of the Terminator line hosting a region of eternal sunrise and sunset, a likely oasis of liquid water and potential biology. The quest to determine which of these fates is true for Kepler 1652b makes it a prime target for the next era of telescopes, which will seek to finally analyze the light filtering through its atmosphere and solve the puzzle of this nearby Earth-sized world. Now we turn our attention to a world that perfectly illustrates the delicate knife-edge balance required for a planet to become a life-giving oasis instead of a scorching wasteland. 36 light-years away in the constellation Vela, the super-Earth known as HD 85512b orbits a K-type orange dwarf star. This stellar host is a calmer, more stable cousin to our Sun, offering a gentler and more consistent flow of energy than the often tempestuous red dwarfs. This peaceful stellar environment is the first point in this planet's favor, providing a stable foundation upon which the delicate edifice of habitability could potentially be built. The planet itself is substantial, with a mass estimated to be at least 3.5 times that of Earth. This places it firmly in the super-Earth category, suggesting a rocky world with a solid surface and gravity significantly stronger than our own. Its most critical characteristic, however, is its precise position within its star's habitable zone. HD 85512b doesn't orbit in the comfortable middle of this region. It skims along the very inner edge, the hottest boundary where the possibility for liquid water begins to fray into the certainty of a runaway greenhouse effect. A year here is blisteringly fast, lasting just 58 Earth days, a testament to how close it must huddle to its star to receive the warmth it does. This precarious location makes the planet's entire potential for life contingent upon one crucial and currently unknown factor: the presence of a reflective cloud cover. Imagine a world where the fate of every ocean hinges on the brightness of its skies. Without a significant layer of clouds, the intense stellar energy beating down on HD 85512b would be absorbed by its surface and trapped by its atmosphere, initiating a catastrophic feedback loop. Temperatures would soar, any oceans would begin to boil, and the resulting water vapor, a potent greenhouse gas itself, would trap even more heat, spiraling the entire world into a Venus-like inferno from which there would be no return. This is the runaway greenhouse effect, and it is the stark destiny for any world that ventures too close to its sun without the proper planetary defenses. But if HD 85512b has managed to develop and maintain a cloud cover covering at least 50% of its atmosphere, the entire equation changes. Those clouds, composed of water droplets or other reflective particles, would act like a global sunshade, bouncing a significant portion of the incoming stellar radiation directly back into space before it can be absorbed and converted into heat. This natural planetary thermostat could lower the average surface temperature by dozens of degrees, potentially creating a stable, temperate climate that allows for large bodies of liquid water to persist. The planet's stronger gravity would be a major asset here, helping it hold onto the substantial atmospheric blanket necessary for such a robust weather system to develop. This isn't a guarantee of habitability, but it is a finely balanced possibility, a testament to how a single planetary feature can mean the difference between a cosmic paradise and a permanent hellscape. HD 85512b serves as a critical test case for our understanding of habitable zones. It forces us to move beyond simple calculations of orbital distance and stellar energy, and to consider the complex, dynamic systems of feedback and regulation that truly determine a world's climate. It demonstrates that the habitable zone is not a binary switch between life and death, but a spectrum of possibilities where geology, atmospheric chemistry, and even meteorology all play an equally important role as astronomy. This world challenges us to broaden our search parameters, to look for planets that might seem too hot at first glance, because with the right atmospheric conditions, they could be just right. And now we arrive at a system so close and so packed with potential that it feels like it's practically on our interstellar doorstep. Just 12 light-years away, a faint red dwarf star known as JJ1061 holds a tight family of at least 3 known planets, 2 of which offer a fascinating comparative study in the search for life. This star is a quiet neighbor, an M-dwarf with remarkably low stellar activity, meaning it doesn't bombard its planets with the life-sterilizing flares that plague so many other systems. This inherent stability is the first and most crucial gift this system offers, providing a peaceful environment where the delicate chemistry of life could potentially begin and persist uninterrupted for billions of years. The 2 most intriguing members of this family are JJ1061c and D. Both are classified as super-Earths, but their similarities largely end there, defined instead by their starkly different positions relative to their star's habitable zone. The inner planet, JJ1061c, is a world of intense heat, orbiting so close to its sun that its surface temperatures are almost certainly scorching. It serves as a fiery sentinel, a reminder of the brutal conditions that exist just a short gravitational distance from the precious temperate region. Its rapid 13-day orbit ensures it is permanently baked, a likely barren rock where any hope for liquid water vanished eons ago. Its sibling, JJ1061d, is the true prize of this system. Orbiting farther out, this planet completes a journey around its star every 13 days, a placement that positions it squarely within what astronomers call the conservative habitable zone. This is a more cautiously defined region, not just the optimistic outer limits where water might theoretically exist, but the sweet spot where conditions are most likely to be truly right for sustaining liquid water on a planetary surface. The amount of stellar energy it receives is tantalizingly similar to what Earth gets from our Sun, an almost perfect energy balance that makes it one of the most promising nearby candidates we have found. What makes JJ1061d particularly compelling is its mass, estimated to be around 1.7 times that of Earth. This is a critical detail. A planet of this mass is almost certain to be rocky, with a solid surface of stone and metal, not a puffy ball of hydrogen and helium gas. You could theoretically stand on it, though you'd feel about 60% heavier under its stronger gravitational pull. This gravity is a double-edged sword. It would sculpt a landscape of lower, more weathered mountains and deeper ocean trenches, but it also provides the planet with a powerful anchor to hold onto something even more vital, a life-sustaining atmosphere. A thick atmosphere is the ultimate climate regulator, the blanket that turns a cold, airless rock into a temperate world. For JJ1061d, this atmosphere would be essential not just for warmth, but also for distributing heat around the globe. Like many planets orbiting close to red dwarfs, it is likely tidally locked, with one side in permanent daylight and the other in endless night. Without an atmosphere, this would create 2 extreme and uninhabitable wastelands. But with a robust gaseous envelope, winds and ocean currents could act as a massive planetary heating system, carrying warmth from the day side to the night side and preventing the atmosphere from freezing solid on the dark hemisphere. This could create a continuous band of temperate conditions around the entire planet, particularly in the eternal twilight of the Terminator line, or it could even moderate the entire globe into a surprisingly stable and Earth-like climate. The combination of its ideal location, its likely rocky composition, the stability of its star, and its incredible proximity to Earth makes JJ1061d a premier target for the next generation of astronomy. At just 12 light-years away, it is one of our closest potentially habitable neighbors. This short distance means the light we receive from its star is relatively strong, giving our telescopes a much better chance to analyze the faint signals that could reveal the secrets of its atmosphere. The upcoming extremely large telescopes on the ground and future space-based observatories will be trained on this system, hoping to detect the chemical fingerprints of water vapor, carbon dioxide, or even potential biosignatures like oxygen and methane in its air. JJ1061d isn't just another entry on a list. It is a tangible, nearby world that represents one of our most accessible opportunities to finally answer the question of whether we are alone in the cosmos. Imagine a world that isn't just like Earth, but is statistically one of the closest matches to our home planet we have ever found in the cosmos. That world is Kepler 442b, a distant exoplanet located over 1,200 light-years away in the constellation Lyra, and it stands as one of the Kepler Space Telescope's most significant and promising discoveries. While many planets on our list offer fascinating but extreme environments, Kepler 442b presents a vision of a world that feels hauntingly familiar, a potential Earth 2.0 that has captivated astronomers with its near-perfect scores on the cosmic checklist for habitability. What makes this planet so special starts with its stellar host. Unlike the red dwarfs that dominate our list, Kepler 442b orbits a K-type star, an orange dwarf. These stars represent a Goldilocks category in themselves. They are smaller, cooler, and longer-lived than our Sun, but significantly larger, warmer, and more stable than the flare-prone M-dwarf red dwarfs. This stellar serenity is a monumental advantage. An orange dwarf provides a steady, gentle flow of energy without the violent, atmosphere-stripping tantrums of its smaller cousins, offering a far more stable and peaceful environment for any potential biosphere to develop and thrive over billions of years. The planet's placement around this stable sun is absolutely ideal. It orbits comfortably within the center of its star's habitable zone, that life-giving region where temperatures could allow liquid water to exist on the surface. But it's not just in the zone, it's in the sweet spot. Scientists calculate the amount of stellar energy a planet receives, a value known as incident flux. For a world to be truly Earth-like, this number needs to be very close to 1, which is the value for Earth. Kepler 442b's incident flux is calculated at about 70% of Earth. This is a fantastic number. It means the planet receives a similar level of warmth as Earth, but slightly less, likely placing it in a perpetual, comfortable autumn-like climate globally, rather than risking the scorching heat of a runaway greenhouse effect. This energy balance is one of the most critical factors elevating its status as a top-tier candidate. Furthermore, its physical characteristics are incredibly promising. Kepler 442b is classified as a super-Earth, but only just. With a radius only about 30% larger than our own planet, it sits right on the cusp between a true Earth twin and the larger super-Earths. This size is crucial because it dramatically increases the probability that it is a rocky world with a solid surface, just like Earth, Venus, or Mars. Statistical studies of planetary mass and radius have been conducted on thousands of exoplanets, and the data shows that planets below 1.6 Earth radii are almost certainly terrestrial, with a composition of rock and metal. Kepler 442b falls well within this limit, leading researchers to conclude with high confidence that it is not a gaseous mini-Neptune, but a world with a familiar landscape of potential continents and ocean basins. All of these factors, its stable K-type star, its perfect position in the habitable zone, its near-ideal energy input, and its almost certain rocky composition combine to give Kepler 442b one of the highest Earth Similarity Index scores ever recorded. The ESI is a scale that quantifies how similar a planet is to Earth, with a perfect match being a score of 1.0. Kepler 442b scores an impressive 0.84, placing it among the very top contenders for a true Earth analog. This isn't just a world that might be habitable under the right conditions. It is a world that, on paper, has all the fundamental ingredients to be a second home. It represents the quiet, statistical hope that planets like ours are not rare flukes, but common gems waiting to be found throughout the galaxy, each one a potential sanctuary for life in the silent, vast expanse of space. And now we reach the final stop on our tour of cosmic possibilities, a world so profoundly alien in its very composition that it challenges our very definition of a planet. 100 light-years away in the constellation Draco, a super-Earth known as TOI 1452b orbits not one, but two small, closely bound stars. This binary system adds a layer of celestial complexity, but it is the planet itself that has astronomers utterly captivated. Recent, meticulous studies of its mass and radius have revealed a startling truth. This world is not primarily made of rock and metal. Its density is incredibly low, a measurement that points to one irresistible conclusion: TOI 1452b is likely a vast global ocean, a water world where the very concept of land is a foreign fantasy. Imagine a planet about 70% larger than Earth and nearly 5 times more massive. On a rocky world like our own, that density would suggest an immense iron core and a crushing gravitational pull. But the data for TOI 1452b tells a completely different story. Its density is consistent with a composition where a staggering fraction of its mass, up to 30%, is liquid water. To put that in perspective, Earth, the so-called blue marble, is less than 1% water by mass. Our deepest oceans are mere puddles compared to the abyss that would envelop this world. Scientists believe the entire surface of TOI 1452b is covered by a single, uninterrupted ocean, potentially hundreds of kilometers deep. There are no continents here, no islands, no shorelines. Just an endless, dark sea stretching from pole to pole under a hazy sky illuminated by twin suns. Beneath the surface, the environment would be unlike anything in our solar system. The pressure at such depths would be immense, creating exotic forms of ice not found on Earth, like ice VI or ice Roman 7. Not frozen water as we know it, but high-density crystalline structures that form under extreme pressure. This could mean the ocean does not have a traditional seafloor of rock. Instead, it might transition gradually into a slushy mantle of these high-pressure ices, a bizarre boundary between liquid and solid. Yet between the surface and this icy barrier, there could exist a layer of liquid water dozens of kilometers thick, a vast, dark, and pressurized abyss. It is within this eternal, sunless deep that the most thrilling possibilities for life emerge. Without sunlight, energy for biology would have to come from elsewhere. The planet's interior, warmed by the residual heat of its formation and the radioactive decay of elements in its core, could drive hydrothermal activity at the water-rock boundary or at the water-ice boundary. These hypothetical vents would spew mineral-rich fluids into the ocean, providing the chemical energy and building blocks to sustain entire ecosystems completely independent of the stars above. This is a scenario we see on a smaller scale at the hydrothermal vents in Earth's deep oceans, where bizarre tube worms, blind shrimp, and unique microbes thrive in total darkness. On TOI 1452b, such life could exist on a planetary scale, evolving in isolation for billions of years in an environment of constant pressure and perpetual night. The life forms that could emerge from such a world might be beyond our wildest imaginings, perhaps buoyant, gelatinous giants drifting through the abyss, or creatures that communicate through bioluminescence in the overwhelming dark. TOI 1452b is a fitting and magnificent conclusion to our journey because it represents the ultimate expansion of the concept of habitability. It is not an Earth twin. It does not orbit in a familiar way. Its environment is utterly foreign, and yet it stands as one of the most compelling places to look for life because it possesses the one ingredient we know is non-negotiable: water, and in unimaginable abundance. It forces us to look beyond our own planetary experience and accept that the universe, in its infinite creativity, can craft living worlds in forms we are only beginning to understand. This distant ocean, shimmering under the light of its twin suns, is a powerful symbol of hope, a reminder that life is tenacious, adaptable, and could be waiting for us in the most unexpected of places, hidden beneath the waves of a truly alien sea. And so our journey across the cosmos comes to a close, leaving us not with a single answer, but with a universe of breathtaking possibilities. We have ventured from our closest stellar neighbor, Proxima Centauri b, to the ancient, wandering world of Kapteyn b, and gazed upon the deep, hidden ocean of TOI 1452b. We have encountered worlds of fire and ice, of perpetual day and endless night, of crushing gravity and global seas. We have seen that a habitable world is not a simple blueprint but a spectrum of incredible diversity, a testament to the universe's boundless creativity. This incredible menagerie of alien environments, from the compact, family-oriented system of TRAPPIST-1 to the solitary, sun-like orbit of Kepler 452b, does more than just fuel our imagination. Each one revolutionizes our scientific understanding. They have taught us that life could thrive not only on pale blue dots like Earth, but in the high-pressure depths of Hycean worlds like K218b, or in the subterranean oceans of icy super-Earths like Kepler 1229b. They have shown us that stable, long-lived stars like the orange dwarfs hosting HD 40307g and Kepler 442b might offer even more promising havens than our own Sun. With every new discovery, the definition of habitable grows broader, richer, and more wondrous. This expanding catalogue of cosmic real estate brings us closer than any generation in history to answering that profound, ancient question: are we alone? We are no longer simply wondering, we are actively hunting. The tools to find the answer are now pointed at the skies. The James Webb Space Telescope and its successors are already beginning to sniff out the atmospheric compositions of these distant orbs, searching for the chemical whispers of biology, the unmistakable cocktail of gases that shouts life. The search is no longer a fantasy, it is a mission, and while we wait for those first paradigm-shattering data points to stream in, we all have a role to play. It begins with simply looking up. The next time you find yourself under a clear, dark sky, remember that those pinpricks of light are not just stars. They are suns, and around them we now know orbit worlds. Some may be barren, others may be hellish, but a precious few, like the 25 we've explored today, could be stirring with the same miraculous phenomenon we call life. Stay curious, follow the discoveries, and never lose that sense of wonder. For the greatest discovery in human history is perhaps just a telescope glance away, waiting for us to finally find our place in a galaxy that may be teeming with company.